Bond behavior of upper reinforcing steel bars in self-compacting concrete beams at shear zone. Abstract self-compacting concrete, SCC, represents an innovation in the building industry due to its workability. This type of concrete flow under its own weight, fill and formwork and pass between bars without need compaction, but the mixture proportions for SCC differ essentially. The higher powder content, limited volume, and nominal maximum size of aggregate, larger quantity of super-plasticizers make design requirements in achieving the self-compacting concrete. The bond between SCC and reinforcing steel bars is major requirement for design of RC structures. The current study investigates the effect of various parameters that affect the bond behavior between SCC and steel rebars at the maximum shear strength zone, such as splice length, concrete cover, and the effect of confining steel. The test results showed that increasing splice length from 50% to 75% LD significantly improved the ductility, energy absorption, and the structural behavior at failure. Increasing stirrups intensity at splice zone decreases the shear cracks at the ends of splice and raise the capacity of specimens and make the failure more ductile. Increasing concrete cover increases the cracks at splice and decrease the capacity of specimens. Keywords: self-compacting concrete, SCC, bond strength, compaction, full-scale beam, lap-spliced bars. 1. Introduction. Bond between concrete and reinforcing bars in a splice is an important requirement for design of RC structures. Within the last 25 years, the interest in SCC grows rapidly, and now it's used in bridges and high-rise building construction. An example of SCC is the two anchorages of Akashi-Kaikyo Bridge, which opened in 1998, and the bridge with the longest span, Indiana the World, 1991 m. The bond between steel and concrete has direct influence on the behavior of reinforced elements in the cracked stage. 19. Deflections are affected by the distribution of bond stresses along the reinforcement bars and by the slip between the steel bar and concrete. Bond was the subject of many studies on SCC, but the conclusions were very contradictory. Some mention that bond strengths of reinforcing bars in SCC are higher than those for NVC, others see no differences between or even lower strengths. Most studies agree that the bond strength of rebars in SCC is larger than that in NVC. Experimental work was done, and analytical equations were proposed by some researchers. There have been several studies to make self-compacting concrete a standard 1-9. The subjects to be solved were summarized as self-compactability testing method, mixed design including acceptance testing method at site, and new type of powder or admixture suitable for SCC. The European Guidelines for SCC3 represents a state-of-the-art document addressed to those SPICE.ERS, designers, purchasers, producers, and users who wish to enhance their expertise and use of SCC. The recommendations have been provided using the wide range of experience and knowledge available to the European Project Group. C. During the last decade, little researches were conducted on bond strength of self-compacting concrete. 17. In 1990, a Torad Azizinamini ETAL1 tested a total of 18 beam specimens with 2 or 3 bars spliced. The variables were a. Concrete compressive strength FO, b. Splice length, and c. Casting position. The results revealed that normalized bond strength decreases, concrete compressive strength increases with a rate of decrease increases as the splice length increases. In the case of NVB, the top bar demonstrated approximately 8% reduction in bond capacity compared to bottom cast bars. As indicated by comparison with the results, top bars, as .NED by the ACI 318-1110, produce higher bond capacity when HSC is utilized. Urlasai and Ozturan 2-Z53 eccentric pull-out test specimens. Specimens were 4 groups, where a single parameter varied in each group. For the .RST3 groups, the parameters were concrete compressive strength, the reinforcing bar diameter and thickness of concrete cover. These parameters varied as 60, 70, 80, and 90 MPa, 8700, 10, 150, 11600, and 13050 psi, 12, 16, 20, and 26 mm, number 4, 5, 6, and 8, and 15, 20, 25, and 30 mm, 5/8, 3/8, 1, and 1-1/8 in, respectively. The parameter of the fourth group was the percentage of web reinforcement that was made up of 3 closed stirrups spaced at 30 mm, 1-3/16 inches, transversely crossing the anchorage length of the longitudinal bars. Web reinforcement varied from no stirrups to stirrups density of 3, 4, and 6 mm, D1, D2, and D4, diameter steel bars. The results showed that the average anchorage bond strength varies with the compressive strength of concrete, as FC 2/3. ACI code slightly underestimates the impact of concrete strength on anchorage bond resistance when applied on HSC, while it overestimates the effect of concrete C cover on anchorage bond resistance when applied on HSC. The research project of Chan et al. Included the testing a RC wall as the pull-out specimen where pull-out reinforcing bars and transverse reinforcement were positioned. Some walls were SCC while others were cast from NVC. The variables were a. Concrete compressive strength F0, b. Height of pull-out bar, effect of top bar, and c. Age of concrete varied from 17H to 28 days. It was concluded that SCC compared to NVC exhibits higher bond to reinforcing rebars and lower reduction in bond strength due to the top rebar effect. The slow improvement of concrete compressive strength and bond strength in SCC at early ages is due to the retarding effect of the carboxylic high-range water-reducing admixture used. Almeida et al. 5 tested 66 beam specimens made from 3 SCC mixes. The variables were a. Maximum aggregate size, and b. SCC ductility. It was found that the bond resistance was not affected by the SCC lack of ductility. It was also found that high-strength concretes have a fragile rupture of the bond connection. Also, unless some con.nement reinforcement is provided, splitting of concrete surrounding the bar will happen as the concrete tension strength is attained. Finally, the desirable failure mode, with yielding or slip of the bar, will not occur. The behavior of the beams was similar in the 3 series of tests, even considering the low ductility of one of the 3 mixes. 12 beam specimens, 2000*300*200 mm, were tested at positive bending. 6 loading system was done to determine the effect of SCC and reinforcement diameter on bond slip characteristics of tension lap slices. The beams of lap splice group were tested with lap spliced bars in the midspan at a region of constant positive bending. The results showed that load transfer within the tension lap spliced bars in SCC in a RC beam was better than that of the tension lap spliced bars in NVC. The SCC beam specimens had generally longer cracks in length than the beams produced from NVC regardless of the reinforcing bar diameter. The project of Cattaneo and Rosati 7 included testing of 27 pull-out specimens containing 1 embedded reinforcement bar. The variables were reinforcement bar diameter, .bur existence and con.nement. 2 types of tests were done, uncon.ned and con.ned pullout. The tests showed a remarkable size effect on bond strength. Smaller bar diameter exhibited a higher strength than the bigger one. The bond strength of SCC was found to be higher than normal strength concrete. The concrete cover, 4.5 b, where b is the bar diameter, was not sufficient to prevent splitting failure in SCC. 2 experimental work. 6 full-scale simply supported beams with cantilever specimens were tested with different configurations under 2-point loads. The main objective of the test program is to investigate the effect of the main parameters. 2.1 Test specimens. The proposed test program has been designed to fulfill the following criteria. 1. Have suppressed the bending failure mode. This is because the program discusses the behavior of bond and shear failure at support at maximum shear. 2. Getting the bond failure of lap splice before yield of bars. 3. Evaluate the applicability of various lap splice equations, in different building codes and standards, for calculating lap splice and self-compacting concrete beams. Table 1 gives a complete description of the test specimens that includes the variables. 2.2 Materials. SCC can be designed to fulfill the requirements of N206 regarding density, strength development, final strength, and durability. Due to the high content of powder, SCC may show more plastic shrinkage or creep than NVC mixes. These aspects should therefore be considered during designing and specifying SCC. Current knowledge of those aspects is limited, and this can be a region requiring further research. We must begin curing the concrete as early as possible. The workability of SCC is higher than the highest class of consistence described within N206 and can be characterized by the following properties: filling ability, passing ability, segregation resistance. A concrete mix can only be classified as self-compacting concrete if the requirements for all three characterized are fulfilled. Many trial mixes were done to have various values of FCU with changing the percentage of W/C, water-cement ratio, an amount of viscosity agent and the final quantities required by weight for 1 cubic meter of fresh concrete for the specimens as given in Table 2. Once all requirements are fulfilled, the mix should be tested at full scale at the concrete plant. Table 3 show the fresh concrete properties of concrete. 2.3 Test Procedure. Specimens used in this research consisted of two groups, 6 R-section self-compacting beams. All beams have a total depth 300 mm, width 200 mm, and length of specimens 2700 mm. Figure 1 and Figure 2 show the geometry and dimensions of the tested specimens. G1 model.jpg. All dimensions in millimeter. Beams cover: B1 equals 20 mm, B2 equals 30 mm, B3 equals 50 mm. 2.4 Instrumentations of specimens. Different types of instrumentations were used to monitor the specimen behavior. The following measurements were recorded during the specimen testing. The actuator load was measured using 400 knots, capacity load cell attached to the movable end of the actuator. Deflections along the beam span and cantilever free end were monitored using 4 dial gauges. The concrete strains at the max shear strength were measured using extensometer and DMEC points, distance between them, 100 mm, and they have been fixed on the concrete surface at maximum bending moment and at mid-span. The reinforcing steel strain was measured at the start, the middle, and the end of splice length using 120 ohm electronic strain gauges. 2.5 Test Setup and Loading Procedure. The test specimens were tested under monotonic load. The load was applied with a uniformly increasing displacement until failure. All specimens were simply supported in 4 points test as beam with cantilever as shown in Figure 3. Each specimen was supported over 2 rigid supports with 1800 mm simple span with 600 mm cantilever span, and load was applied using 300 knots capacity hydraulic actuator with max stroke 100 mm. The load was divided to 2 concentrated loads 1500 mm apart, at cantilever free end and beam midspan, using rigid steel spreader beam. The actuator was driven in displacement control and the load was applied against a reaction steel frame. Data form load cell, dial gauges, straining gauges, and extensometer were recorded manually during the test. 3.1 Influence of confinement at splice. 3.1.1 Load capacity. The recorded ultimate load of beam B5 and B6 was about 94.4% and 78% of B4. It can be attributed to the low confinement of beam B6, which enable this beam to be more brittle at failure. The spacing between stirrups at lap zone, F10 at 200 mm, at the region of maximum shear where the ends of lap splice act as crack initiators and cause the first crack at load 30 knots and enable this beam lower moment capacity. From the area under the load deflection curves of both beams B4 and B5 in Figure 5, it was found that this area of B5 is about 78% of B4 and the area of B6 is about 37% of B4, which means that beam B4 has larger ductility. This can be correlated to the influence of higher stirrups intensity within the region of maximum shear strength, unconstant shear strength. It also noted that the contribution of stirrups in improving ductility in beams, normal strength self-compacting concrete, is significant because of the large lateral deformation of NSSCC. These results coincide with that obtained by Ferguson and Breen 20, where they stated that stirrups eliminate the sudden and violent failure. Also, these results match with Rashad's 21 results, who stated that stirrups prevent the sudden disruption of equilibrium at splice zones. 3.1.2 Energy absorption. Figure 6 shows that the energy absorption decreases with increasing the spacing between stirrups at the lap splice, decreasing confinement at splice zone from 10 at 100 mm to 10 at 200 mm, decreased the EA to 62% according to beam B4. 3.1.3 Stress along lap splice and bond stress at splice. The steel stress was affected by confinement at splice zone, where the maximum steel stress was 586 MPa of B4, with stirrups F10 at 100 mm at splice. The steel stress of B5 and B6 is about 87% and 79% of B4. The smaller steel stress of beams B6 in comparison to B4 can be attributed to the high level of confinement at splice zone of B4 than others, which enable this beam to exhibit larger steel stress before failure and reach the yield point. From figure 7 shows that beam B4 had the maximum bond stress value, which the bond stress of beams B5 and B6 is about 93% and 85% of B1. Which means that increasing confinement increases bond stress, although the three beams had same splice length equal to 75% LD. 3.2 Influence of concrete cover. 3.2.1 Load capacity. The recorded ultimate load of beam B2 and B3 was about 80% and 50% of B4. It can be attributed to that increasing the concrete cover decreased the effective depth from 20 mm to 50 mm, which led to decreasing the failure load. It was noted that the cover, 20 mm, enabled the beam B1 to behave with a more ductility manner. Increase the concrete cover from 20 mm to 50 mm, increase significantly the max capacity and max deflection by 50% and 56% respectively, as shown in figure 8. 3.2.2 Energy absorption. Figure 9 shows that the energy absorption decreases with increasing the concrete cover. Increasing concrete cover from 20 to 50 mm decreased the EA to 76% according to beam B1. Figure 9, Energy absorption for Group 1, B1, B2, B3. 3.2.3 Stress along lap splice and bond stress at splice. The steel stress was affected by concrete cover, where the maximum steel stress was 480 MPa of B1, with cover 20 mm. The steel stress of B2 and B3 is about 85% and 60% of B1. The smaller steel stress of beams B3 in comparison to B1 can be attributed to the smaller cover of B1 than others, which enable this beam to exhibit larger steel stress before failure. From figure 10 shows that beam B1 had the maximum bond stress value, which the bond stress of beams B2 and B3 is about 86% and 62% of B1. Which means that increasing concrete cover decreases the bond stress, although the three beams had splice length equal to 50% LD. 3.3 Influence of lap length in SCC beams. 3.3.1 Load capacity. The recorded ultimate load of beam B2 was about 80% of B4. It can be attributed to that increasing splice length led to increasing the failure load. The smaller ductility of B2 compared with that of beam B4 is due to the smaller ultimate load of B2. The beam B2 had lower deflection than beam B4. Which can be stated that the beam, with splice 75% LD, enable the beam to more ductile manner and enable beam to improving the moment capacity. 3.3.2 Energy absorption. Figure 12 shows that the energy absorption decreases with decreasing the splice length from 75 to 25%. Limited decreased the EA to 64% according to beam B4. 4 Conclusions. Based on the experimental and analytical results of 6 beams with cantilever specimens constructed from SCC with different lap splice configurations, the following conclusions was drawn. 1. Increasing splice length from 50% to 75% LD, significantly improve failure load, ductility, energy absorption, and the structural behavior at failure, such as mode of failure, splice length, 75% LD, have more ductility and energy absorption. 2. Increasing stirrups intensity at splice zone from 10 at 200 to 10 at 100 mm decreases the shear cracks at the ends of splice and raise the capacity of specimens by 22% and make the failure more ductile. The ductility and energy absorption increased by 45% and 63% respectively. Increasing stirrups intensity increases the ultimate bond stress by 14%. 3. Increasing concrete cover from 20 to 50 mm increases the cracks at splice and decrease the capacity of specimens and make the failure more brittle, as well as the bond strength was not good.